Okay, so this is, it's going to be a very lightweight talk after a paper by No Ito, by Sebastian Bubeck and Mark Sellke, posted a week ago, maybe. To the archive. And the title is Law of Robustness for, was it just via Isoperimetry? Okay. Okay, so let's start. When in machine learning, we have a concept of memorization. What's memorization? Maybe first let me, let me start by what is expressivity. Usually we want to learn some function from among some class of possible functions. We're trying to minimize some loss among some class of functions, and then if we put the learning part aside and we just look at a class of functions, it's natural to ask, first of all, what's the expressivity of this class? What functions can actually be expressed as neural networks, depth 2 networks, maybe like just think of your favorite family and you can ask, what kind of functions can be expressed using them. There's also a concept of memorization where we don't want to.
Expressiveness isn't defined. You mean functions that are close to this?
Right. Yeah. Functions that are close. You could.
The set of functions. These are the functions that you can express exactly.
That's just the family of functions.
So
sure.
Some functions that are close.
So of close can depends on whatever. Sure.
The coding probably can fill out.
Right. So,
maybe say you define it.
Yeah, I think it doesn't matter so much. So what's memorization? Memorization is just given the data points xi and yi, is there a function f in our class such that, let's say, it's close, f of xi is close to yi. There could be any loss function, but in this talk, let's just talk about square loss. So we could just ask, for given a family of functions, for which data sets can we just fit the data with our family? And usually the family of functions has some parameter here, which is, so it's usually a family of families of functions. So if you think about neural networks, for example, this P can stand for the depth, the width. In general, this will be the number of parameters that we have in order to express a function in the family, okay? And then we can just ask, how large should P be? So, or how large should P be so that there exists f such that this holds. Okay?
So that how large f?
No, just a parameter. So how many parameters do you need?
So yeah.
Okay.
Okay.
When you say, so how large should P be?
Oh, I see. So, oh, how many parameters?
How many parameters do I need to have in my family in order to fit the data?
If you like.
Okay, so it's natural to expect, I mean, if we're being very informal, that well, what should be the relation between P and the other parameters in order to be able to fit endpoints of data? It's if P is bigger than N, or right, bigger than maybe N times some constant, but in general, if P is bigger than N or just a bit bigger, then we can fit the data. Just by counting degrees of freedom. Of course, I said nothing yet. But
the other direction is more obvious. If P is much smaller than N, it probably cannot.
Yes, the other direction is, I guess, easier, because if this is, so I didn't say what the dependence of F on the parameters are. It could be some kind of a Peano curve, but if it's not some kind of Peano curve, then this we just get some manifold with respect to P, and then P smaller than N is probably makes things impossible. And in this talk, we're going to ask the question, how large should P be so that we can fit the data, but we can also do it robustly? And there are several meanings one can give to robustly, but the meaning that we're going to give is that I want F to be nice, and in particular, I want it to be Lipschitz. So in this talk, how large should P be? So that we can fit with F that is Lipschitz. So you can just assume your functions are Lipschitz, and then you can ask, are there nice families of Lipschitz functions such that I can always fit the data with one of them? And we're actually going to be talking about lower bounds, and we're going to establish that for families of Lipschitz functions, it's actually hard to fit the data using only n degrees of freedom, and we'll have actually something more quantitative than that. But let's.
Are you going to make any hypothesis on the data, the pairs?
We are. Yeah. So let's start with a few examples before we go to the actual theorem. And I want to talk. So first of all, some examples of families of functions. So a nice example is two-layer neural networks. What are these? So this is a very natural family. Fix K, a number, and some activation function, some nonlinear function sigma from R to R, and then let's consider functions of the form f of x is the sum over neurons. So each summand here will be called a neuron. I goes between 1 and k. We have k neurons, each of the form some number alpha I, and then I take here sigma of x dot wi. Actually, let's call it wi. plus bi. So here, what is P? The number of parameters that I need for this thing. These are vectors in, so if F is from RD to R, then these guys are vectors in RD. And these are just numbers. So I have D plus 2 numbers per neuron. So here P is D plus 2 times K. Okay. Natural choices of sigma that people usually care about and we'll just briefly mention are just, so sigma of x is just x to some L, just some polynomial, some monomial. Sigma of x is x times the indicator that x is positive. This is called the rectified linear unit. Okay, let's just
The sigma you would like to put there is the threshold function at 0. I mean, either the neuron is active or not, but it's various ways of smoothing it, of making it continuous. I mean,
sure, but like I'm not sure if the sigma, if I'd rather put like, if there's any reason to, the original models just had this, but this is a way to smooth this so that we can, this is Lipschitz. On this way, but yeah, I guess the main reason is on this we can actually do gradient descent with respect to the parameters here. If it's just an indicator, it's much harder to try to optimize over the family.
Before that, models of neurons where it either fires or not, and
sure.
If it's above the threshold, a linear threshold, it fires, otherwise it doesn't. That's
sure.
That's discontinuous, and that's ways of smoothing it.
Yeah, right.
Who knows what happens in the body?
Yeah, I agree. Actually, I want to try to discuss that later, some of that. Okay, so what did I want to, so yeah, so now did I, let me just keep this one example of a family and now discuss some.
Is this 2 layers or just 1 layer? Like you called it 2 layer, but you activate sigma only 1.
Yeah, so like this is 1 layer and the other is where I'm adding those up.
Okay.
It's like 2 linear layers and 1 non-linear layer. I agree that one should call this 1 layer, but the jargon is that this is 2 layers. They call it 2 layers or 1. Yeah, how many linear layers?
Just think about a linear circuit. Circuit does the distance.
Okay.
Right? The input layers, then you add some subsets of them, then you add some subsets of these, then you add some. So that's a natural depth of a linear circuit. It's like a linear operator A, you compute it by depth D circuit. If you can write A as the product of B sub B1 times B2 times etc. BD. That's a natural way to define the depth of a linear circuit, right? How many you have that this layer is just doing simply parallel, right? So what you do now is that inside each, that to every gate you do this nonlinearity on itself. It's not talking to anybody else, right? It's a sigma operator, each intermediate, sort of gate in your circuit. So the number of layers is just a number of linear operators you compose. You compose two linear operators, so it's just with or without the non-linearity.
So in general, the number of times, the number of layers on which sigma acts is going to be the number of total layers minus 1.
Yeah. just think of a picture that you have the input x1 to x3, and then you have some, gates adding subsets of them. It's another, and then you have some gates adding subsets of them.
How many times are you composing? Some, yeah.
It's non-linearity. It's Weizmann individual.
Okay, so let's just to so what I want to do now is give two very basic extreme examples, which are supposed to illustrate the trade-off between having more parameters than the minimal ones that we need to fit the function and making the function Lipschitz. So what I want to illustrate is that there is probably some phenomenon going on, so that if it might be the case that P only needs to be as big as N, but if it's only as big as N, you might not be able to memorize with the Lipschitz function. And if you want the function with which you memorize to be also Lipschitz, you probably should pay by having more degrees of freedom in your family than you need. Okay? So to illustrate this, let me give two simple examples. Yeah.
Maybe more precisely, just if people have never seen this, you mean Lipschitz with uniformly bounded Lipschitz constant, independent of N and P.
Yeah. The Lipschitz constant should obviously, I mean, let me talk a bit later about why we would even care about having Lipschitz, about the fitting with Lipschitz functions. But
just the word memorization. I mean, it looks like approximation to me.
So the point is you don't approximate. So the assumption is maybe that xi and yi came from some function you're trying to learn. Maybe yi is g of some xi for some function g you're trying to learn. Approximating g over all the, approximating with respect to all the population distribution means this is called like expressivity of g. But here you don't want to, our goal is much more modest. We don't want to learn the whole function. We just want to fit the data. We just want to memorize the labels of the data we actually got. This is why it's called memorization.
I see, because all it produces is if you know the xi's, you can remember
the yi's, but it doesn't say anything about generalizing. Yeah, exactly. Just encoding the yi's of as with this, with the parameter.
So the word.
Yeah. This is
okay. Fine.
Okay.
There are tight connections between the ability to express the data this way and learn. I mean, it's almost equivalent.
Right.
But sometimes this is called memorization because you imagine that you fit the data kind of, let's say epsilon is even 0, but it's white noise outside the data. So you do nothing but memorize the data rather than learn the underlying population. Yeah, exactly. But just a comment about Avi's comment that that it's almost equivalent to compressing the data. So this paper is going to make a case for why overparameterization is good. Usually, when you compare it to compressing the data, the claim you're making is use as little parameters as you can so that you compress the data. If the entropy is like the entropy of the data, then you probably did some good compression and you've learned something. So here it's kind of like the opposite philosophy. Yes, exactly. Okay, so just two very simple extreme examples. So case 1, I want to look at the case that the number of degrees of freedom is exactly equal to n, and I want also this to be equal to the dimension of the space. So I have d points in R to the d, and I want to fit them using these guys. Now, if p is equal to n, then k is just equal to 1. I mean, okay, P is equal to n order of n plus 2, whatever. And in this case, we can actually think about linear activations. Okay, so we can fit d points in d dimensions with an affine function. Okay, but in this case, let's try to understand what the Lipschitz constant is, and assume that xi, so we have the xi's and yi's. So xi, suppose that it's uniform on the sphere, on the unit sphere, and yi is independent from xi and uniform in -1, 1. Okay, so we're just trying to fit noise in RD. And my question is, what's going to be the Lipschitz? So, this is optimal in the sense that P is just n.
Sort of very trivial. Do you mean plus or minus 1 or you mean interval?
This just plus and minus 1. If I could do this curly bracket, then, not the interval. Yeah, you could do the interval, and it's going to be essentially the same, but just Bernoulli. Yeah. So of course we can fit with a linear function unless with probability 1, these guys will be linearly independent, so everything is fine. But let's try to understand what the Lipschitz constant is going to be. Okay, so we're going to claim that when we don't use so many parameters, this is not going to be Lipschitz. So what happens is, well, any guess what the Lipschitz function is? Does anyone see it? What did you say? No? Root n, yeah. So let's look at all the points where yi is equal 1, all the xi's where yi is equal 1. Those are, they lie on some subspace. So we can rotate things so they all lie on this subspace. So xi is such that yi is equal 1 are here. And the yi's such that, the xi's such that yi is equal to -1 are, suppose they lie here. Those subspaces don't have to be parallel to each other. Just let's look at the affine span. How do you know that they are even separated? Yeah, you're saying you don't. But let's even think. Okay, just to make things even a bit easier, let's
They're separated on
yeah.
the sphere.
Yeah, they're separated on the sphere.
You might want to just draw them as sort of crossing because they cross at the origin.
Yeah, but I think this sketch is actually more informative in the sense that, so I want a linear function which is, it's -1 on this subspace, and it's +1 on this subspace, right? And well, so it's -1 in particular at the center of mass of all the xi's, and it's +1 at the center of mass of all the yi's. And how far is the center of mass of the xi's from the center of mass from the yi's? Well, if xi's have norm 1 and there's d of them, then the center of mass has norm 1/√d, right? Just because okay, 1/d sum xi. This is the center of mass, 1/d sum xi. How big is this thing? So it's 1/d squared, and then the correlations are 0. So if I put the sum outside, it's 1/d squared times d. So the norm square is 1/d. So this is 1 over root d from the origin, and also this. So this distance is 1 over root d. But I know that, you know, this point is 1 and this point is minus 1. Okay, good. See, Avi, no matter what I'm talking about, I can make it like much slower than anyone expected. I'm really good at this. Okay. Okay, and then I claim that in the other extremal case where P is equal to n times d, meaning I have 1 neuron for every data point, I just need to fit 1 data point per neuron, I can make the Lipschitz constant equal to 1 rather than, so here the Lipschitz is omega of root d. And in this case, I claim that I can make the Lipschitz constant 1. Any ideas how? I'm still looking at uniformly distributed points on the sphere. Labels are plus minus 1. Now I can fit every point with 1 neuron. How can I do it so that, and I'll also suppose that I don't have too many points. So suppose that n is at most something like e to the O of d. Then, like a nice thing in high dimensions is that for every point here, with high probability, all of the other points, if I draw a cap from the origin to the point, this radius is 1, but suppose like this distance is 1/2 or something, then this cap has surface area something like e to the minus d. Right? So the probability that I have 2 points falling in the same cap like this is very small. So I can just, you know, if I have, for example, ReLU, I can make a neuron that's just 0 up to here, and then just increases linearly from this point on. And they can just fit this point. And, you know, none of these caps will cross each other. Okay? So here we can make okay. So now the conjecture that Sebastian Bubeck had in a paper with Lee and Nagraj a year ago, I guess, is, well, essentially one needs the Lipschitz function. In order to memorize, one needs that the Lipschitz function is at least root n d over p. So here, if p, when p was exactly n, we had root d. When p was n times d, we had 1. And they conjectured that there's this interpolation in between.
But what exactly is p formally when I'm not talking about neural nets?
Very good question. We'll get to it in a minute. But they actually had the conjecture specifically for two-layer neural nets.
Okay.
And actually, so the result in the new paper, it's one of the theorems where
if you try to think about two-layer neural net, it seems like a hard problem. But if you formulate the statement correctly, which in this case is in a much more general framework, then it's actually much easier to see what the proof should be. So
can I make a remark about this?
You can always make a remark.
Great, thank you. Okay, so one thing is that this interpolation threshold p equals n is something that even for non-noisy data empirically is the worst you'll ever do for generalization. Right, so if you look at the double descent curve, the usual infinite variance peak is at p equals n. But there's a triple descent curve for neural networks, and the second peak is at p equals nd. Number of parameters equals number of data points rather than width equals number of data points.
Nice. I didn't know that.
Yeah,
so maybe before you continue, let me just let me do it just so everyone knows what you're talking about. Okay. So there's usually this picture of, so what's the motivation to such a conjecture? So in machine learning, in the classical, like the pre-neural network era, you used to have this picture where you don't want the number of parameters in the system to be too large. If it's too small, you just can't fit any function at all, and then you just get anything. So maybe suppose here is the, I guess, generalization error. Okay, what's a generalization error? It's really the expectation over the population. So suppose that xi, yi are all distributed given some underlying distribution, and this is just the error between the f that you find and So this is, how inaccurate you are over all the population rather than just the data points. If p is very small, then you definitely have some big error. And in the classical case, when you increase p, you get something better and better. And then there is an optimal point, but then you over-parameterize. You just have too many degrees of freedom, and you just, instead of fitting the signal, you just fit the noise, which gives you some function which is kind of like very off the. So now it keeps increasing. Okay, this is the classical picture. And many people are trying to understand why. So empirically, with deep neural networks, you have a double descent where you still have this picture, but then at some point, maybe some other point, it increases, and then it just decreases below this minimum and seems to converge to something. And maybe it'll increase at some point when p is super large. Probably not, actually, but it's kind of surprising that you kind of really need to overfit the data. In particular, this point is so here p is going to be much bigger than n, right? So as you said, in the double descent, what happens is that so this point, I guess, is more or less at p equals to n, right?
No, the peak is at p equals n. The worst.
The peak is at p equals to n. Yeah, I'm okay.
Yeah, that's the worst. That's somehow when your covariance of the data is the most important.
I see. So here you don't overfit, but okay, here it kind of looks like the classical regime. Here you can fit the data exactly, but you're losing something because like you get a crazy function fitting the data. But when you increase p, people like to say it as you add regularization. You still fit the data, of course, in all of this, but you fit the data in a way that somehow regularizes the function, right?
The point of
and then
is that to the right, it's not necessarily monotone. There's actually another hump.
So you're saying,
okay, so at some point it actually increases.
So it increases again and goes down, you know, at p equals nd. At least you know. So there's
Okay.
There's at least two natural thresholds, and it's unclear how many there are.
So like this.
That's right. And in fact, the best thing is between p equals n and p equals nd, and it's good, but not quite as good to the right somehow.
So you're saying if I have one neuron per data point, I can just fit the data in a stupid way, like we described with the caps before. And then, or maybe you get something like completely dumb and so here, I guess you just have no reason to interpolate because you can just fit every data point separately.
They
Okay.
would say that there to the right, you don't learn a representation because you don't need to. Whereas in the middle, you can fit, but you can't use the neurons.
But I don't understand why it goes down again. So I've never seen this picture. Very nice. So why it goes up when p is like crazily big, I understand, but why should it go down again? I don't know.
I'll
Okay.
tell you why the humps happen. They happen when a certain matrix is almost not invertible.
Well, but what exactly do we see in this graph? Like, is this the best choice of parameters?
This graph is, you want to learn how to differentiate between cats and dogs. You have a family of functions. You do
some learning process.
Yeah. You do gradient descent over your family, and then this is what happens when you test it over not the data points for which you trained, but on like new data points. So over the population, essentially. Okay. So now, of course, if I just look at how I fit the data, you know, it'll just be like 0 by here and keep being 0. But I mean, yeah, if I look at the testing set rather than the training set, so the entire population, then it actually gets worse.
And the data that you were talking about is with something like one of these two-layer neural nets or some other model.
So I mean, so there's a theory paper which takes random data like this with high input dimension. They do some kind of high dimensional, very complicated random matrix theory.
So is this just linear? Do you just fit like a product of linear layers?
You take the NTK to the kernel.
I see. So I see.
So they sort of assume.
So it's very plausible actually to assume that if you don't do NTK, you're not going to see this, because this is seems like kind of specific to when you can exactly solve those linear equations in a way. So it's okay. Maybe let's discuss this later. There's this, when you do optimization, there is a two-phase, right? First, you learn the best linear approximation, and then you start changing the non-linear things. And when the linear thing can fit, this is exactly here, I guess, and then you see this, but if you're not in the NTK, okay, let's, it's really interesting too.
Like the left part, the double descent without that second hump I added, that's just an empirical fact for lots of models and real data that we don't fully know how to explain, except for in some special cases.
The first one. The first one, there's hundreds and hundreds of papers. You just keep seeing this phenomenon. And very, very few theoretical papers. Yeah, but
you get to this point where you're not really learning anything that's useful for them. I'm surprised that it's that low, that hump. I guess it's just that there's not.
Okay, so let me just comment that, okay, this is, I'm being recorded, but I'll say it still. So, I mean, what the theorem I'm going to show you is, I think, is a beautiful theorem. Sebastian and Mark claim that this theorem is kind of like, makes a case to why one would need overparameterization. I claim that it's a beautiful theorem, but it actually makes a case against overparameterization. But let me explain to you later. Yeah, I'd really like to have some time to maybe make a discussion about this. Okay, so to formulate the theorem, I need just one definition. A measure mu on RD is C concentrated if for every one Lipschitz test function, we have that the probability or the measure of the set where F differs from its expectation by at least T is at most e to the minus t squared over c. Let's put a 2 here. It doesn't matter so much. Okay, so it has a Lipschitz functions have sub-Gaussian tails. This is a very natural definition. Some examples that satisfy it. If you have a product measure of nice enough variables, maybe the main case to think about is if the uniform measure on the sphere. Yeah, so this thing is going to be 1 over root d concentrated.
Oh, I see. You're going to do it like that.
I want to put a c square here. So in particular, I want to say, C is going to be the variance of one Lipschitz functions, but also I'm going to have a sub-Gaussian tail. Okay. So in particular, good. And okay, I do need one more definition. Let me put it here just so that I have more space for the theorem. Another definition. If my family of functions is of the form f sub w, where w is in some omega subset of R to the P. So this is a way to use P parameters to define a function. Is J Lipschitz representation if just for every x in RD, I have that fwx minus fw1x minus fw2x is at most jw1 minus w2. So
this answers the question that you had, or so what's a reasonable way to parameterize a family of functions? So we just want the function to be Lipschitz in L infinity with respect to the parameter. And it's not hard to check that if you look at two neural networks, you have something like this with J equals 2. Also deep neural networks. What other families do you like? What? This is not only for depth 2. So also deep neural networks are going to satisfy this.
Yeah, the J will change.
The J will change, but we will only care about, so the dependence on J is going to be logarithmic in the theorem. So we actually, like, deep neural networks are going to be just fine.
Are you sure
that it's going to be logarithmic?
Parameters. You want to really look at the L2 norms in each layer, maybe of the difference. Something like okay, it doesn't matter. You might have to take some slightly different.
Maybe okay. Let me. Let me, instead of RD, let me say X is in some bounded set, okay? Because this might be a problem, but also this set can be like, we'll only have things involving log J, so also the size of B can be polynomial, and we're not going to care about it. It's going to only add logarithmic terms. Okay. So now I can finally say what the theorem is. The theorem is not bullshit, but it's by Bubeck and Sellke. It's basically saying if I have, IID sampled from some measure D on RD times R such that Xi are such that, I guess, the marginal of D onto the X coordinate is C concentrated. And let F admit a J Lipschitz representation with P degrees of freedom. Now we only have to assume also something on the Y's. So if the Y's are just constant, of course, we can fit anything. We want the Yi's to have enough noise. Finally, assume that the variance of Yi conditioned on the fact that Xi is equal to any X is at least sigma squared. So this means that, even if I condition, I still have sigma squared variance, meaning that I have some noise in my data. Okay, I have a noise of size sigma squared. And actually,
let's also assume that this is bounded. The yi's are bounded. Then with high probability, for every f in my family such that f approximates the y's a little better than this sigma squared, I have that the Lipschitz constant of f is at least something like epsilon is omega of epsilon, and now root nd over p.
When I can explain the variance, once you restrict xi equal to x, don't you have only one y?
No, so this is I mean,
Because of the distribution. Okay.
Yeah.
Sorry.
Yeah, so think about yi as some g of xi plus noise. This noise has to have variance at least sigma squared, okay? Okay, let's prove this theorem. Let me first explain the proof of a weaker thing that will give you, I think, a very clear intuition on why this is true, okay? So suppose, let's suppose yi are just pure noise, okay?
With hypothesis, first of all, it's over the distribution of over D, the hypothesis, right? Over D. D is the only random variable.
Yes, yes.
It's just over the distribution. Second, this hypothesis is going to be exponential. How it?
It's going to be exponential. Yeah. So let's for now just a toy case, but it's almost like as general as, so suppose that the yi's are just Bernoulli minus 1, 1. Okay, so I only have noise. In general, I have to have a noise which is like, okay, I guess this has some dependence on sigma, okay? But think of sigma as being order 1, okay? Then let's see how to prove this. Then for any f, which is 1 Lipschitz, okay, maybe let's first define the event A to be the event that the sum over all I of yi, the average is, say, at most, I don't know, 0.1. So those are just IID Bernoullis. The average by the law of large numbers is like, 0. This by Hefding or your favorite sub-Gaussian inequality is, has probability something like e to the minus omega of n. Okay, I guess this is clear. And here is the point. Under A, let's fix some.
probability of 1 and -1 are both half.
Yes. Let's fix f and ask what's the probability that f.
Yeah, it's just central limit here. It says it's very close to.
Yeah, sorry. Let's fix f and ask what's the probability that f fits our data. Now, here is the observation. We know that that mu is C concentrated and f is Lipschitz. Let's only look at one Lipschitz function. So the whole point of concentration is that f has now, well, f is very concentrated. It's 1 over root d concentrated. So either there's a very large, so f cannot be very close to both -1 and 1 on large sets. Either the set where f is close to -1 is very small, or the set where f is close to 1 is very small. Okay? Then by concentration, either mu of the set that f, mu is the measure, d sub x, yeah, of the set where f of x is at least 1 minus epsilon is at most e to the minus omega of d, or the same thing with -1 plus epsilon. Just because, you know, most points of f are close to the expectation, to be a distance 1 to the expectation costs e to the minus d. Okay, so either the set where it's close to 1 is very small, or the set where it's close to -1 is very small. And then, you know, we fixed f. Let's condition on the event A. So half the points are 1, half the points are -1. And now what's the probability that all the points which have, you know, this sign fall exactly here? For every point, the probability is e to the minus d. So the probability that all the points fall here is like e to the minus nd. Okay? Under A, for all such f, the probability that f fits psi yi fits the data is at most e to the minus n times d.
When you define the concentration in the statement that you just raised, you wanted it to be C over square root of D concentrated. You're putting the D in the exponent.
Did I write C concentrated?
Yeah, for the statement.
For the statement, I wrote C. No, it needs to be C over root D concentrated. Sorry. Yeah. I mean, that's really the crucial point. Yeah. Good. So now, if we just try to discretize, so, you know, let's look at this bipartite graph, where here we kind of try to cover all the set F, and here.
You're doing an epsilon net over F.
Yeah, exactly. So, you know, the point is every point on the left side, every function covers some points whose measure, so this set has measure at most. just e to the minus omega and d. And
What do you earlier when you say under A?
Assuming that they are balanced,
assuming that the event A, conditioned on the event A. Okay. The yi's and xi's are independent in this case. So I can just condition and the xi's are still independent. So, you know, every f covers something of this measure. And the question is, how many f do we actually have to check to do a union bound? And the point is that, you know, we have one Lipschitz representation in R to the P, J Lipschitz representation. So the covering number is at most, well, suppose that suppose that omega is, each coordinate is in some minus poly and d. Is bounded by some poly and d, then we get that the covering number is, the epsilon covering number is poly and d over epsilon to the p. And then to do a union bound, we just want over epsilon, sorry. And then to do a union bound, we just want the product of this and this. Yeah, sorry, my handwriting is really bad today. To be small. So we just get the condition that, you know, n, the covering number is at most, and j is also here. Yeah, so we just get that, you know, P needs to be at least n d over log j over epsilon, I guess. ND. Okay. Epsilon is not in the log. I think you're right that epsilon shouldn't be in the log.
Yeah.
But what am I missing? I'm missing something because the covering number. Yeah, I think the epsilon. Okay, listen, this was just a toy example where the guys were just plus and minus 1, and then approximating by epsilon is, you know, or approximating by 1/2 is already like as hard as approximating by epsilon.
There were also
yeah, so you say you just don't see.
Yeah.
Maybe.
Yeah, so
you have to do the probability of your various events, and there the epsilon is not in the logarithm
Yeah.
of the probability. So the p has to beat it with the epsilon outside.
Again.
So like, you know, you have the event A, for example.
Right.
So its probability is exponential, but it's like, you know, either they like epsilon squared.
Right. You have to beat this with the epsilon as well, but this is just e to the minus n instead of e to the minus nd. So epsilon is still here. I think it's still going to be in the log. Yeah, I think it's fine. But okay, I'm like really good at taking much more time than is reasonable. So let me now prove the actual theorem. The proof is not going to take so much, but for me, everything takes a lot. So good.
But this is okay, right? This proof was fairly, like nothing is happening here. Yeah, I mean, no, I think it's really remarkable to find that they found the right assumption, and also we simplified it, but yeah, like this was pretty simple, I guess you agree. Okay, so now we want something more general. You know, the yi's can still be correlated with f of xi. What we're going to do is the following thing. So let's define some events. Let's define the event A. Okay, first let's define yi to be equal to some g of xi plus zi in a way that this is deterministic given xi, and this is just noise. Okay, so I want such that the expectation of zi given xi is 0. And recall that our assumption is that the variance of zi is at least sigma squared. Now, let's look at the event A, that the average of the zi squared is at least sigma square minus epsilon, say over 10 or something. And the event B, that the zi's are not too uncorrelated with the gi's. So 1 over n sum zi g xi is at least minus epsilon over 10. Note that these events do not, I mean, okay, they just depend on the data. They don't depend on the function f. And claim the probability that both A and B hold is at least e to the minus omega of n. 1 minus e to the minus e. So this is just, I guess both of these are just Heffding inequality. The zi's are bounded between -1 and 1. The variance is sigma squared. So, you know, the expectation of this sum square is just sigma squared. And then I want, you know, this is the large deviation.
Yeah, here you have epsilon already.
Right. Here I do have epsilon. Exactly. That's going to be the point. Right. Maybe. Yeah, exactly. So it's n over epsilon. It's n epsilon squared. Right. This is going to be the real dependence on epsilon. Okay, so we're fine with this, I guess. Now, for every f in our family of functions, let's define the event C sub f associated with f as the event that the correlation between now f of xi and zi is at most epsilon over 10.
Okay. And I claim that if both A and B and C sub F hold, then it must be the case that we're not too correlated. It must be the case that the sum is, well, at least sigma square minus epsilon. Recall that we wanted to say that it cannot be the case that the sum is less than this and also the function is Lipschitz. Okay? So this is just a deterministic statement. Let's see why it's true. Let's define, okay, I guess. G is, you know, the vector gx1 up to gxn. Let's normalize it by 1 over root n. Z is 1 over root n, the vector z1 up to zn. And y is the vector of the y, no, f is the vector of the f's. Then what we want to say is that this is big, which means that, well, this is just the norm squared of f minus g minus z. We want to say that this is big. This is equal to z squared not even this. It's really like it's parallelogram. What, call it what you will. It's like what?
Triangle has 3 sides, and parallelogram
Yeah, so yeah, you're right. So every parallelogram is also, it's just 2 triangle inequalities stuck together. Plus, what do I have? ZG minus ZF plus F minus G squared. I opened it correctly. I need some 2's. Yeah, who cares about 2's? And okay, and I claim that this is bigger or equal under A, B, and CF. Let's see. So A tells me that, what does A tell me? A tells me that this is at least sigma square minus epsilon over 10. B tells me that this is at most epsilon over 5. Sorry, this is at most minus epsilon over, at least minus epsilon over 5. CF tells me that this is at most epsilon over 5. And this is positive. Okay. Good. So look, I mean, we defined, okay, so we have A and B. They have high probability and they don't depend on F. If we just establish that C sub F has a very high probability for every F, then we'll just be able to cover F and use a union bound. So all we have left to do is establish that the probability of C of F, note that it's not enough to say that C of F is also of probability 1 minus e to the minus n. Just e to the minus n is not enough because the size of our net is going to be like e to the p, which we want it to be e to the n times d. Okay, so we want probability of CF is at least 1 minus e to the minus omega of n times d, rather than just n. And this will, the proof will be completed as before by a net argument, right? This will imply the theorem. Okay. Okay, so what we want, we establish that if both this, so for every F, if this holds, then we cannot approximate. Okay. I guess maybe let me add here for every F in F, which is 1 Lipschitz. So what we want to say in the end is that there does not exist a Lipschitz function such that where is it written? Such that the reverse inequality here holds, right? Such that it's kind of correlated with the noise. Okay. And the claim says that, well, it's enough to check that for every Lipschitz function, A and B and also CF hold. Now, A and B already hold with high probability and don't depend on F. So if we establish that for every Lipschitz function also CF holds for all of them simultaneously, then we're done. Because then there is just no Lipschitz function for which the reverse inequality holds. Okay. So
how do you get?
So how do you get all F?
The omega and d. It's like the.
So the point is again that we establish this for one particular F, and then again we cover the set of F's by, covering our RP, the set of parameters, and then using the fact that the covering is that we have a Lipschitz constant between the parameter space and the F. Okay, like we did before. I guess I didn't. Okay, so we just want this, and let's see. Here's the point. So what was CF? CF was, we're interested in this quantity, Zi f of xi. And we want to say that this guy is usually very, very small. Instead, let's first look at this quantity.
But the intuition is that f is around its mean with exponential in d probability.
Exactly. Yeah. I mean, it's going to be two lines. So, yeah. f is around its mean with exponential d probability, but we're also summing n terms. This gives us an n, boom, we're done. Yeah. So look at this sum. Every summand here, like this, so let's call this WRI. The point is that Ri is by definition 1 over root d sub-Gaussian. Why? Because by definition of the sub-Gaussianity of the measure mu, this guy without the zi is 1 over root d sub-Gaussian. We know that f of x, with respect to generating xi, f of xi is like 1 over root d close to its mean with sub-Gaussian tail.
With respect to this square root d measure.
Yes.
Square root d concentrated measure.
Yes. I mean, xi is distributed in a measure that's square 1 over root d concentrated, which exactly says that this guy is 1 over root d sub-Gaussian, not including the zi. But well, the zi doesn't do anything. It's bounded between -1 and 1. And then there is a fact saying that, so well-known fact, you can prove it in many ways, for example, by using the Laplace transform. If Wi is, if Wi are IID C sub-Gaussian, then 1 over root n, the sum of Wi is, well, O of C sub-Gaussian, maybe 10C sub-Gaussian. And that's it. So like this guy is 1 over root d. What?
Why are these guys independent?
By definition, the xi's and the zi's. Yeah. It's just You just sample independent examples from your distribution. Yeah. So like with this fact, we get that this guy. I don't know. I need to give them names. Zi is, well, all the zi's are independent, but zi is not necessarily independent from the xi, but it's between -1 and 1. So even if you choose something between -1 and 1 adversarially, and you multiply it by a sub-Gaussian thing, you're still sub-Gaussian. In fact, you only improve the, Okay, so
you generate, maybe the worst case, just taking all of them one.
Exactly.
Otherwise,
yeah. Well, I mean, the worst case, I mean, we're still using the fact that the expectation of each one of this is 0, right? Okay. So yeah. So you cannot pick it adversarially to, kill the cancellations. So each one of these is sub-Gaussian with expectation 0.
The expectation of Zi, Gi. Sorry, the expectation of Zi is 0.
The expectation is of Zi even conditioned on f of xi is 0. There could be a dependence, but you see. But it could not create an expectation. and it could not destroy the sub-Gaussianity. Yeah. So this is 1 over root ND sub-Gaussian, but it's not quite what we wanted. We wanted a bound on the probability that only this, without these expectations, is big. But well, you see, these expectations are, they again don't depend, like if I just take the sum. So now let's look at the sum of Zi expectation of F. Well, this doesn't depend on like, it only depends on this one parameter, which is the expectation of F. And in fact, this is bounded by, you know, the absolute value of the sum of Zi. And again, by your favorite inequality.
The expectation of F is bounded?
Well, you know, we want to fit those. If F is not bounded at some point, we can always round it to plus and minus 1, because the yi's are in the interval plus and minus 1. So assume with a clause of generality that F is truncated. But good point. F, we never said it. Yeah, so since this happens, we have, this implies that the probability that this guy is at least epsilon, if we average, epsilon over 10 is at most e to the minus n epsilon squared again, omega, whatever, of n epsilon squared. And that's it, we're done. So under this event, which does not depend on F, we have that, like, so, okay, so I kind of cheated by saying that P probability of C of F is big. I also have to assume that this event happens, but this event does not depend on F. So I'm not sure actually what they do. Yeah, but I'm sure what they do is not very different than this. But I think, okay, we can look. But in any case, let's call this event D, if you want. Yeah, I just realized that you need to do it. And then, you know, given D, the probability, we're fine, because this guy is sub-Gaussian.
That's a big event. That's 1 minus
the
greater.
Yeah. It's the opposite. But let's put it like this, just to be consistent with the rest. Yeah. Okay. So CF, yeah, under D. So let's say probability that CF minus D, CF complement minus D is at most. Okay. So sorry for confusing you. Yeah. So I think we're done, because now under D, we just have to take care of this guy, which we established is 1 over root ND sub-Gaussian. So the probability that it's at least epsilon is like e to the minus epsilon squared ND, which is what we wanted. Okay. Yeah, sorry for like taking an hour and a half for something that should have taken 20 minutes. But yeah. But okay, now let me just, I guess, you know, the point, okay, maybe just one comment. Almost the same proof says that you don't need to assume that. So we made a pretty strong assumption that the xi's are distributed in something which is very concentrated. So they can't, if they're just distributed in the standard Gaussian, this gives nothing. They need to be distributed in something like the sphere, so that one Lipschitz functions have variance 1 over d and not 1. Okay? And when, you know, it's not clear at all how to check empirically if, you know, the distribution over natural images or whatever is concentrated. Does it look more like the sphere or more like the standard Gaussian in terms of concentration? Or maybe it's not concentrated at all, right? Maybe natural images have images with a dog in them and images with a cat in them, and both are really like non-expanding sets, which, okay, there are images of cat and dog, but I mean, clearly it's a non-expanding set because I can, for example, count how many objects are in the image. Like, are there 2 animals or 3 or 4? And each of these connected components is definitely like disconnected from the other. So there is no concentration, but their theorem still works if mu is a mixture of not too many measures which are themselves 1 over root d concentrated. So you could write, so it's okay if mu is like the sum of mu I, where mu I are 1 over root d concentrated, and the number of summands I goes from 1 to k. The number of summands just has to be not too much bigger than n. So it has to be at most something like n epsilon squared, which is pretty strong. So we can decompose it to a pretty large number of summands. The proof like is, I mean, I don't think there is a point showing it because there is, you just kind of, the only difference is here.
The sufficiently small, it doesn't affect the bound at all. The trade-off between Lipschitz and the other.
Again, so if
this parameter k, that is just low, it's not smoothly affecting their bound. It's just if it's small enough, then it doesn't affect it at all.
Yes, exactly. If it's small enough, it just doesn't affect it at all. So you just need, you know, that in each one of these components, you have at least 1 over epsilon square points that fall. But still, okay, now what I guess I want to claim off the record, even though I'm being recorded, is no. I mean, I think it's nice to, you know, this is, you can send a link to Sebastian. So the way the way I'm thinking about it, so here's the point. I mean, this only makes, so what this is telling us is that we need to over-parameterize so that the function with which we fit is Lipschitz. But if the function that we're trying to learn in the first place is Lipschitz also, then concentration tells us that it's almost constant. So it's either the case that we're trying to differentiate between cat and dog. Okay, so there's a function, we want to learn something that's like 0 if it's a cat and 1 if it's a dog. If it's Lipschitz in the first place, it means that all the examples we're learning are just either all of them are cats or all of them are dogs, which is, you know, kind of pointless. Now, it could be the case that we're trying to learn a function which is not Lipschitz, but we're arguing that still it makes sense that the function with which we learn, the function we fit, is still Lipschitz, right? But I think, you know, that what this shows essentially is that in order for all of this to work, we want our function to fit in a non-trivial way, to be non-trivially correlated with the IID noise and not with the function itself. So basically what this theorem is saying, that if we want to correlate a function with IID noise and we want it to be Lipschitz, then we need to over-parameterize. But I think in this case, where the ZIs are just IID noise, and they are really the big ones, they have size sigma, it makes much more sense that if the function g is Lipschitz, and therefore g is almost constant, and the ZIs are of constant order, then it doesn't make sense that we over-parameterize no matter what. So
But isn't the point is that, what the effects of life, I don't know machine learning, maybe people have experience.
Me neither, but.
Yeah, or Boris, etc. It seems that the things we are learning typically are not legit and have noise. Right? That's a fact, that's one fact number one. The second is that the things we are learning with, like DeepNet, are legit. They are pretty smooth if you if you insist on this, for optimization, say, you insist on these, values or something, right? Which make it sort of smooth.
So
just to say, if those two assumptions hold, then, this result is meaningful. That, it's a limitation of the way we learn that we are using smooth functions to learn non-smooth things with noise, with non-trivial noise, and therefore the number of examples that this needs, parameters it needs, must be large.
Why do you say that you are learning using
So that's the nature of the, let's say the Twolayer network. They are J, whatever.
So I mean, you see here though that they really have to be Lipschitz in a way, if they were, instead of one Lipschitz, I would write root D Lipschitz, then all of this would be completely, but
The point is that it's very large.
But in the neural networks that we're learning in practice are just poly-D Lipschitz. They're not like one, I don't think there's any, definitely. ReLU itself is one Lipschitz, but when we're learning with ReLUs, the weight you put in front of the ReLU or inside, doesn't matter, both affect the Lipschitz constant, are usually like yeah, maybe what I know that people are looking at is usually the space where all the weights are like poly-D. If the weights are one, in which case this is not even, so if they're Lipschitz, the weights can't even be one because they add up when we add neurons. So I think like it's very restrictive.
The weights are not normalized. You say they are of magnitude.
So usually the weights are normalized in a way that if you take a random point x and you plug it into f, the f of x will have variance O of 1. And this normalization usually corresponds to, if you have k neurons, every neuron contributes 1 over root k magnitude, like so that the variance of every neuron is 1 over k, and they're almost independent. And then the Lipschitz constant is, also like 1 over root k, but when you add them up, it could add up to root k rather than to 1. And this is, this is also, it depends if the parameter space is the sphere. I think it's more natural to think of the parameter space as being the standard Gaussian rather than the sphere. And then if you have unit vectors inside the ReLUs, then the variance of a single ReLU is 1. If it was the sphere, then inside the ReLUs, you don't need to have unit vectors. You need to have vectors of size root D. And then even one neuron is not Lipschitz. So
that's a critical question. What is the smoothness of a real life.
How big is D?
So D, okay. So D, if you have images of 100 pixels by 100 pixels, you a priori would say D is 100 times 100, whatever that is. But the actual dimensionality is usually much lower because you can take the picture and smooth it a bit. You'd usually just look at the Fourier, not too high frequencies, blah blah blah. In their paper, actually, they have some discussion where they, I don't know if I can find it right now, but there is some discussion about what the actual dimensionality is, but like it's really not clear. So if all the coordinates are between 0 and 1 and not between -1/√d and +1/√d, like the case of the sphere, then you shouldn't be talking about 1 Lipschitz functions. You should be talking about 1/√d Lipschitz functions. And these, the point is that we're talking about functions such that the Lipschitz constant only allows an oscillation of O of 1. So if you take 2 points whose distance is like the diameter of the space, the difference between f of x and f of y can only be O of 1. And this, and you think, I think, this seems to me like a smaller class than what you usually want to fit with. It should be the case that the variance of f over the data is omega of 1. So you're saying the variance of f over the data is the same order as the entire oscillation of f, which, it could be that it's true in practice, but I'd be surprised if such a thing is true.
So I think it's sort of complicated in the sense that if you take a neural network that people just train in the real world.
But because nobody hears us, maybe it's good to take this discussion.
I'm very happy to. Yeah, it makes sense.
Can you thank yourself?
What?
Can you thank yourself and clap?